Okay, so first of all, we shall finish our topic that we started yesterday. Let me remind you that our lemma, I'll call it lemma 1. Maybe it was not lemma 1, but lemma 1 of, okay, I shall call it lemma A. Okay. So lemma A was the following. Let L be a smooth of class C2, the smooth C2 foliation of codimension 1 on a compact, simply connected manifold. So manifold, then L possesses a vanishing cycle. Vanishing cycle. Cool. What is that? Let me remind you. Vanishing cycle. It is the following thing. You remember this foliation on the torus. Okay, now we have a solid torus. Its boundary is a leaf, and you take a closed curve gamma 0 on the boundary, which is not homotopic to 0 on the torus. And our foliation is like that. The leaves are, okay, and finally it comes here. And so gamma 0 can be approximated by gamma t's, which are homotopic to 0 in their leaves. So vanishing cycle is an embedded closed curve, not homotopic to 0 in its leaf, which can be approximated by closed curves in nearby leaves that are homotopic to 0. Okay? And such thing on a simply connected manifold always exists. The proof was a sort of rough, but after all, it is very in the spirit of Poincar, Bendixson, and Haefliger theorems. Okay. Now, second lemma B, we are going to discuss today, says the following. Let L be a codimension 1 smooth C2 foliation on a compact threefold. So now we suppose that our manifold is of dimension 3. But for this lemma, well, we don't need that M is simply connected, yes? Okay, but just for this lemma. So we have a C2, a smooth and of class C2 foliation on a compact three-dimensional manifold. Suppose that some leaf of L contains a vanishing circle. A vanishing circle. Then well, let me say this. Then L admits a non-zero transverse measure. Okay, we know that proof. How we are going to prove this? We know that the set of transverse measures is in one-to-one correspondence with the set of foliated cycles. Let me recall you that foliated cycle is a current of integration along the leaves of foliation, but which is closed. D of C is 0. Okay. Now you will see how it arrives. So in fact, we shall prove that there is a foliated cycle. And how we shall prove this? Okay, I am going to use this picture. Just let me make it a little bit more clear. So what I'm doing, now I will use dimension 3. So this is a good picture. And what I'm going to do, so I have this, I know that I have vanishing cycle, so I have a nearby gamma t. Okay, I shall go this. And let me denote by dt the disk which is bounded by gamma t. Yes? I know that for t bigger than 0 and up to 1, my curves bound disk. Only gamma 0 is not bounding anything. Okay? So for t for t bigger than 0, I have a disk. So now, two observations. The length of the gamma t is the boundary of this disk. Okay, on the corresponding leaf. On the corresponding leaf, I will denote by LT, and the final leaf as L0. Okay. Now I choose some Riemannian metric on my manifold. Okay, and now since gamma t, well, they just converge to gamma 0. This is a continuous family of curves. I have that the length of gamma t tend to the length of gamma 0 when t goes to 0. Yeah, for me it will be important that the lengths of the boundary stay bounded. Okay. But the areas of dt goes to plus infinity. Okay, proof is slightly long, but intuitively, why? Well, suppose that the areas stay bounded. So you have some circles, they bound some disk, which are in the leaves, they are not arbitrary, they behave very good. Circles converge to the circle, but then these guys, they cannot escape. They will converge again to a disk. And this is impossible because gamma 0 doesn't bound any disk. Roughly, this is an argument. So we have 2 points. And now what we can do, we can define a foliated current. If you even don't know what is foliated current, you forgot, but it doesn't matter. It should be a functional on 2 forms. So our foliation is of dimension 2. So omega now is a 2 form on M. And we defined a functional on a 2 form in a natural way. We just integrate this form over the disk. Okay? And we divide this by the area of the disk. Good. It is a linear functional on the space of forms, continuous, so on. And it is somehow acts along the foliation. So it's directed by our foliation because it integrates form along a piece of our foliation. So that means it's a foliation current. And the mass of this current, mass, is 1. So what is that? Mass of the current is the supremum of the values on forms divided by the norm of the form. Norm should be not 0. So you have a metric on your manifold, so you can measure vectors, you can measure covectors, you can measure forms. And then every form has a norm. And so this is a norm. And now we have a family of currents of mass 1, and there is a theorem which says that if you have a bounded family of currents of bounded mass, then it is compact. You can subtract a converging sequence. So there exists a converging sequence of parameters going to 0 such that CTN converge to some current C as Tn goes to 0. Converge, that means that they converge on any form. So it means that CTN evaluated on a test form converge to C omega. And since the mass were 1, the mass of C is 1. Well, in particular, this is a non-zero current. This is important. So we got a non-zero current directed by our foliation, and I claim that this current is closed. Okay? I want to prove that D of C is 0. Only for that current I can produce then a transverse measure. Well, so I take one form alpha, and I need to prove that this is 0. So this is equal to 1 over, to the limit 1 over area of D. N when n goes to Tn goes to 0. Integral over dTn of omega. By Green's formula, I'm sorry, of d alpha, of course. By Green's formula, this integral is an integral over the boundary, therefore over our curve gamma n of alpha, and limit when Tn goes to 0, 1 over the area of dTn. But now, this guy turns to 0. Area goes to infinity to 1, and this stays bounded because the lengths of the curves are bounded. So this limit is 0. Okay. Well, if no questions, please, if any questions.
So the convergent subsequence is some sort of
Yes, yes, it's some sort of compactness theorem. The currents of bounded mass, this set is pretty compact. You can subtract.
And so you have a threefold. Where is it used that it's only
Here, when I defined, so I used that my vanishing cycle, the vanishing cycle is a curve. It can bound something two-dimensional. Would I have this curve on a higher dimension, then I don't know what it bounds. And thus, having bounded disk, I can produce current. Okay. Well, so, and we know by yesterday's lecture, we know that we have a transverse measure. If we have such current, we have the transverse measure such that this current is roughly integration with respect to this transverse measure. Okay, somehow. Okay, and this measure is not 0 because our current is not 0. Well, now we are prepared to prove the theorem of Novikov. Which says the following: let L be a smooth C2 foliation of codimension 1. So originally it was stated on a simply connected 3 manifold. But since then the Poincar hypothesis was proved, and we know that the only simply connected threefold is sphere. Okay? So on sphere, on S3. Okay? Then L possesses a compact leaf. So there is a compact leaf. So the situation is as on this picture. You have a vanishing cycle, and then we can produce a compact leaf. Okay, proof. Proof. By lemma A, we have a vanishing cycle in some leaf. By lemma B, we have a transverse measure. Okay, so let mu be a transverse measure. So we use already simple connectivity of our threefold, and we use already that it is a threefold, it's not a higher dimension. Both things we already use. So this is a sphere. So let mu be the transverse measure, non-zero transverse measure for our foliation. So it is not zero, it has some support. What is support of the transverse measure? Let me recall you. So what is transverse measure? You have some transversalis, T, and you have Ti here on the flow box Ui, and you have a measure here, and this measure has some support. Some support of the measure is a complement to the open set where this measure is zero. Okay, this support is not empty, our measure is not zero. So there are leaves which cutting this support. And these leaves, the union of such leaves, of all such leaves, over all transversalities, I am finished my sentence and then I stop. The union of these leaves which are cutting supports of mu I is a support of M. The support of M is some collection of leaves where this M is not zero. It's a closed invariant set, invariant in the sense that with every point it contains the whole leaf which passes through this point. Okay? Now, so as I said, we have a non-zero measure, and therefore the support of this measure contains some leaf. Okay, so there exists leaf L0 which is in the support of mu. I want to prove that that leaf is compact. This I want to prove. Suppose it is not. If it is not compact, then there is a flow box which is cutted by this leaf infinitely many times. Because suppose we have only finitely many flow boxes on our compact manifold. Okay? Suppose that our leaf cuts each flow box finite number of times. Then it is compact. This leaf is compact. Yes? Therefore, there is a flow box which it cuts, but in fact I need 2 times. Okay, but infinitely many. So it like that. This is our flow box. Okay. It's finished. And this is our leaf, cutting this flow box at least 2 times. Now, what I can do? I can take 2 points, let's say P0 and let's say P1. And now, these points are on the same leaf, and leaf is connected. So I can join them by a curve. So I can find some curve which starts at P0 and ends at P1. And this curve, gamma, is inside of my leaf. Now, what I can do, I can look on this picture as follows. Now I have a problem, I am a bad artist, but imagine that you have a curve on the leaf. starting at one point, ending at the second point. A leaf is something two-dimensional. So near this curve, your leaf is a bend. Just you can draw a narrow bend near your curve. Okay? On the surface. Right? And now on the nearby leaves, you can cut the same bend. You will have some family of these bends. Yes? And then you can deform this curve to make it transverse. So your picture is like that. Now I make it straight. So my curve is like that. It is in the bend. And I have family of bends, continuous. Okay? And now I can do the following thing. I can make like that a little bit. And my curve will be transverse. Okay? And now I shall obtain, so of course I moved, this was P0, this was P1. I moved a little bit starting and ending point, a little bit. So moving a little bit starting and ending points. Okay, let's them. I displaced them. One, and it does not matter where. One and second one. No. This is my new P0 and my new P1. And I know that I have a curve from P0 to P1 which is transverse. But no problem, I can close it now. And I got a transverse curve. So using the fact that some flow box is intersected by my leaf at least 2 times, I produced a transverse curve. A curve which is transverse to our foliation. Again, I use dimension 3. Okay? And now this curve, now we had a lemma. We had a lemma C. So if a transverse manifold, it was in any dimension. If you have a transverse manifold to a foliation which cuts the support such that n intersects the support of the transverse measure, then this n is not homologous to 0 in corresponding homology group. Okay? Well, this is our case. We have a curve which cuts L0, which is in support. So we can apply this lemma, and we can conclude that the homology class of our curve is not 0, well, in the first homology group. But our manifold is simply connected. Well, it's sphere, simply connected, and this group is 0. Contradiction. Okay. Well, so the first part of my course is finished. So I proved 3 famous theorems in foliation theory: Poincar, Bendixson, Haefliger, and Novikov. And in the course of discussions, you might observe what are important notions and important objects which appeared. Why it is important? Because now we start holomorphic foliations, and you may ask, okay, holomorphic foliation, and so what we want to know about this? What would be natural questions about holomorphic foliations? Yes, something serious question, not because we want to, I don't know what, but now there is a huge history, 100 years history behind this, and so what was the problems? The problems was this, which I proved you. So we saw that we have the following notions: holonomy, and in the Poincar-Bendixson theorem we saw that we got a limiting cycle, and the Poincaré first return map, which is a holonomy map, is contracting. I was not talking on this too much, but it is contracting because it is the limit of the trajectory. So if you have a trajectory, then it goes like that. It approaches. And that and holonomy map, so h of x will be closer to the reference point, to P. So holonomy map is contracting. And so such cycle, such curve, one can say it is a contracting curve for the holonomy. Second thing which we saw is a vanishing cycle. We saw that, well, it is a very interesting object, okay, here, and it produces, at the end, it produces compact leaves, which of course are of primary interest in anything which you know about foliations. Of course, you might say me that vanishing cycles, they produce directed currents, they produce transverse measures, blah, blah. All these are technical things. Geometrical things are vanishing cycles and compact leaves. The original proof of Novikov does not use this transverse measure and foliated currents. It's purely geometrical, but it's very complicated, very long. Okay, now?
What year was it proved? When was it proved?
In 65, plus minus 2 years. Well, so now we go to holomorphic foliations. Now our manifold M is complex, and okay, we shall suppose it is compact. A holomorphic foliation is defined in the same manner as a real foliation. So we have a family of, we have a collection of connected subsets of M such that first they are mutually disjoint, the union is a Hopf manifold, and the most important thing, they are locally open sets in corresponding CP. No, manifold compact of dimension n bigger or equal than 2. And so for every point Z in M, there is a flow box. There is a neighborhood U of point, B-holomorphism, phi from U to some open V in CP, such that the plugs phi of L alpha intersected with U are Z P plus 1 equal to C1, C plus C1, Zn equal to Cn for some constants, yes? So locally, picture is the same. This is U, these are the sets, and we can redress this picture to get some polydisk. For example, you can always suppose that V is a polydisk, and these sets are sub-polydisks of appropriate dimension, of dimension P. So this is delta N, which is our V, and these are delta P's. Okay? So that means that every leaf of this foliation is a complex manifold of dimension P, but in general it is not a submanifold of M. Yeah, it can be dense in M, for example. Most leaves are dense for most foliations. Okay, now I had some plan to speak about general foliations, and then I thought, well, but I don't think it would be appropriate. So let me restrict myself to the case of foliations of dimension 1, foliations by remote surfaces. It's a naive and nice subject. You can see this all somehow. And for the first, when you are watching this for the first time, this would be useful. Now, so holomorphic, now P is 1. So when P is 1, when dimension of leaves is 1, dimension of M can be arbitrary. Okay? So when P is 1, we say that L is a foliation, is a smooth holomorphic foliation. Smooth means it has no singular points. Holomorphic is sufficiently smooth itself, but it doesn't have singularities. So this thing does not have singularities. It's a smooth holomorphic foliation by Riemann surfaces. Or by curves, by complex curves. One uses this terminology even often. So what is the leaf of such foliation? Well, it's something like that. And then it goes somewhere, and the same here. And it never ends, usually, yes, if it is not a compact leaf, yes. So this is a leaf, or the typical leaf of our foliation. Leaf passing through point Z shall be denoted as LZ. Okay? Now, there is another way to define holomorphic foliation by curves, and this way gives us possibility to define also singular holomorphic foliations. Namely, holomorphic foliation, so this is the second definition. This is definition 1. Now, the definition 2. Holomorphic foliation by curves, holomorphic foliation by curves on M.
Can we try a new pen? Because it's
Oh yes, I'm sorry.
No, it's already
Okay, thank you. Now I don't say smooth holomorphic foliation. Now I'm going to define also singular. So holomorphic foliation by curves on M is given by a covering by an open covering Uj. Our M is compact, then covering is finite, but in general it is not finite. Open covering Uj and holomorphic vector fields Vj. So they are sections of they are holomorphic sections of the tangent over Uj of the tangent bundle. So vector fields, holomorphic vector fields, such that, now look, if you have two open sets and you have a holomorphic vector field here and holomorphic vector field here, then they should agree, these vector fields. They should be proportional on the intersection, such that Vj is equal to the Hij Vi on the intersection, where these transition functions are never vanishing. So Hij belongs to the sheaf of non-vanishing holomorphic functions. Now, that means that they never vanish, that's all. Okay? So you have a collection of vector fields on open sets which agree on intersections. Integral curves of these vector fields will define your foliation outside of the singularity set. So singularity set of this foliation is a set of Z such that Vg of Z is 0. Now, it does not depend on G, yes, because of this condition. So if there is a point in the intersection, and if Vg is 0 at this point, then Vi is also 0, because Vg and Vi are proportional with a non-zero coefficient of proportionality. Okay? This is an analytic set. This is an analytic set. And it can be made of codimension at least 2. Why is that? Well, suppose Vj in local coordinates is written as aj1 d over dz1 plus ajn d over dzn. Yeah? It's a holomorphic vector field. Suppose it vanishes somewhere. If it vanishes along some hypersurface, along analytic set of codimension 1, then you can, that means that all coefficients vanish on this hypersurface, and you can divide all these coefficients by the equation of this hypersurface. If you divide, you got a proportional vector field. So foliation will be the same. And therefore, you can assume that codimension of the singular set is at least 2. In the case of dimension 2 on compact complex surfaces, when I say complex surface, I mean complex manifold of complex dimension 2. Okay? So in this case of complex surfaces, that means that it is a finite set. Okay? And after saying that, okay, leaves. Leaves are defined as a solution of differential equations, yes? So function, let's say, from the unit disk to our manifold is a piece of leaf if dz over d lambda is v of z of lambda for all lambda in D. These are solutions of these differential equations. Well, as it was in the case of foliation by curves on surfaces. Okay? Now, after saying that, I will assume from this point the singular set is empty. So, why is that? Because the topics which I'm going to discuss with you, they don't see singular set. All what I will say you is true for all foliations, also for singular ones. But the exposition in the singular case is much more technical and somehow irrelevant. The ideas you will see on the smooth case. And it is simple for the first time not to think about singular foliation. Well, what can be singularity of the foliation? Well, let me say once more. You can take a radial foliation in C2. Okay? So it has singularity at 0. Okay, so it can be defined by vector field d over d z1, d over d z2, and z1 plus z2, I think. Okay. This vector field is everywhere tangent to the leaves and vanishes at 0. Yes? And this is a typical picture of it. But there are more complicated things than that. Okay. Now, what is one of main questions which one wants to understand in holomorphic foliations? Yeah, so let's go to the Poincar-Bendixson theorem. So what was the point there? We looked for the limit set of the trajectory. Okay, we can do the same here. The limit set of a leaf, limit of L, is a union, how to write this, okay, of all limits of all sequences in this leaf which go to infinity. What does that mean, that sequence go to infinity in some leaf? That means it leaves every compact of this leaf. So if leaf is compact, then there is no limit set, that leaf is compact. But if leaf is not compact, then you take a sequence which leaves every compact in this leaf, and you go and consider all cluster points of this sequence. And all this is the limit set. It's the same as with trajectories. So again, I must change this thing. And Well, one can describe this as a intersection over all compacts in our leaf of L minus compact closure. So you threw away a compact from your leaf, you take the closure of this. This can be, it can be the whole manifold, in fact. Okay? And then you intersect this by all compacts. Well, of course, it is sufficient to take intersections by some exhausting sequence of compacts. Yes. Okay. And now the central question is, what is this limit set? In the case of the Poincar-Bendixson theorem, we saw that the limit set is a polycycle. No, or a singular point, or a polycycle. Of course, all these questions are relevant, even more relevant in the case of singular foliations. But, okay, as I told you, I'm not going to consider singular foliations. Now, my first aim is to divide all holomorphic foliations by curves on compact manifolds into three classes, three disjoint classes. And for that, I will need to introduce some almost metric form adapted to the foliation. So the next topic is taming forms and directed currents. Well, what is directed current we already know. It's a foliated current. In the complex case, it's the same. Okay. Now, taming form. Denote by lambda pp r of m all forms of b degree pp on our complex manifold which are real. Okay. Form of b degree pp is real if its conjugate is itself. Okay. This is a subspace of 2p forms on M, real. Okay. Now, such form is called positive if its restriction for any local submanifold L of dimension p. This is a local submanifold of M of dimension p. Some piece of p-dimensional manifold. So if you restrict, you obtain not a number, but a number depending on coordinates. Well, you understand. You can say if this number is positive or not. So it should be positive. So the form is, the PP form is positive if its restriction to any p-dimensional submanifold is a positive function. Okay. The same can be formulated as follows. For any theta 1, theta n minus p, 1, 0 forms on M. The form wedge omega with this, okay, traditionally one writes I over 2, theta 1 bar, and so on, I over 2, theta n minus p, theta I minus p bar. Why I? To make these pieces real. So this form should be, this is again a form of all these degrees, is again a function, okay, up to change of coordinates, so this should be positive. So this is the same, okay. And now we need the following definition. A 1-1 form omega is said to be L positive. Positive for this foliation, not positive in general, but with respect to L. Or one says that omega is a taming form. For L. Okay, I'm finishing. If okay, a restriction of omega to any leaf is a positive function. It gives you an area form on the leaf, but this is not very precise. So in fact, for any 1-1 vector V tangent to the foliation, our form on I over 2 V bar is not only positive, but is bounded by some constant bigger than 0, independent on, well, any vector tangent and Z, independent on Z. For any 1-1 vector of the length 1. So you fix some Hermitian metric. Okay, so taming form gives you an area form on leaves. Okay, that's it. Thank you.